Alright guys, we're going to be doing H2Se on this one. So the first thing we want to do is count the number of valence electrons. We see that Se has 6, hydrogen has 1, there's 2 of them, so we're going to have 8 valence electrons.
So now we know that we have 48 electrons.
Makes 4 pairs.
Place those around the iodines.
We're going to go ahead and draw the Lewis structure with Se on the central atom. Get your lone pairs. So the Vesper structure is pretty much going to be the same. Just a little in more detail. So if we look at the central atom, we can see that the electron geometry would be an a tetrahedron. But since we only have 2 bonding pairs, the molecular geometry is going to be bent. Couldn't delete these, so let's just make these clear.
So you add those together, 48 total electrons. So now that we know that we have 48 electrons, we can start them around the iodines here.
Since these 2 hydrogen atoms are in the same plane, we don't need any wedges or anything else to show that it's going out because it's in the same plane. So this is going to be the Vesper structure right here. So typically, molecule with the tetrahedral electron geometry would have bond angles at 109.5 degrees. But since we only have 2, these angles right here are going to be less than 109.5. I want to assume that it's similar to the angle of water, right? Because water would pretty much be the same with the oxygen atom at the center and 2 lone pairs and then have 2 bonded hydrogens. So since it's similar to a water molecule, I want to assume that this bond angle is about 104.5 degrees. And the reason for this 104.5, which is not a typical tetrahedral geometry, is because we have these lone pairs that are pushing these bonding pairs closer in. So that's why this angle right here gets smaller than 109.5. So now we're going to move on to a box diagram to show how the selenium atom is going to bond to these 2 hydrogen atoms in regards to their electron orbitals. So you want to start off by drawing orbitals for both of these atoms, and we know selenium's valence shell is at 4p.
Now the S is filled up on the 3s orbital. Here.
And we have the hydrogen atom with the valence shell or its only shell, in fact. So let's fill up this box diagram for selenium. So we have S, So we have the box diagram for hydrogen, and there's going to be two of these. So we know that one hydrogen is going to go here, and then there's going to be another one that goes into here. So there's not going to be need for an electron, a selenium, to be promoted because there's already two spaces open. But in order for selenium to make bonds, it's going to have to hybridize its electron orbitals into SPs. So let's see what's going on with selenium. We have an S shell. It's going to combine with P's. And it's going to make 4 sp3s. So when we combine these orbitals, this is what selenium will look like. And as we can see, this has a tetrahedral geometry, but we have the H's are going to come into right here, these spots.
Now moving on to our box diagrams, where we will show hybridization and the promotion of such electrons.
But in terms of its molecular geometry, we're going to have a bent shape because we have two lone pairs. So let's go ahead and draw that.
Leading to the 4p orbital getting partially filled, the remaining 4 electrons. For the next step, we go straight into hybridization without promoting any electrons to the excited state, because there are only 2 spaces left in which hydrogen is going to take up in the bonding state.
Now we are ready to hybridize.
So we have
We're going to hybridize our
selenium's hybridization orbitals. And now these hydrogens are ready to make bonds. With selenium.
And here we will have an sp3 sp3d2 orbital. Where
Go ahead and draw the
iodine has 6
electrons,
so
electron pairs.
each one of these sp3d2 serves as one orbital for each one of those groups. So now we can bring it into hybridization. 1, 2, 3, 4, 5, and 6 groups. And right now we only have.
Here you go, just had to clean it up a little bit. So now,
Electron, which will come in and bond.
now we can see that selenium has its lone pairs and an sp3 orbital at the top, and then it has 2 sp3 orbitals filled up by 2 hydrogen atoms. So in terms of the electron geometry for selenium, it would be a tetrahedral, as we can see on top. But since we're only focused on the molecular geometry, you can see that it's bent. And this angle right here is going to be less than 109.5 because, as mentioned earlier,
Unpaired electron will go into
the electron geometry for selenium
and begin to fill
is a tetrahedron, which is 109.5. But that's if all the electron groups were equal, meaning if they were all lone pairs or if they were all bonded pairs. But in this case, we have two lone pairs and we have two bonding pairs. So this bonding pair is going to repulse these bonding groups and push them down smaller to be 109.5, which, as mentioned earlier, is similar to the molecule of water, which is about 104.5. And here goes a picture of H2Se in 3D form. And although it looks like these two are in different planes, this is just to give details in its 3D form, but these are actually really in the same plane. So there you go. There goes H2Se.